Usually I'm supposed to click this off when we get the recording going. There we go. Looks like it's time. Welcome back, everyone. I'm a few seconds behind, but I don't think that'll matter too much. The announcements are pretty much here on the Moodle website, like we're used to seeing. But before we get started, any questions at all that folks would like to bring up? Okay, maybe probably the better announcement we should talk about right away, just though it's out of the way, is that we're coming up to our very first exam. As far as the exam goes, the exam information is that it's going to cover up to section 2.4. Major reason for that, of leaving off section 2.5, even though we were so close to getting it done, is when I try to write an exam, I like to ask questions on the exam that are informed by the actual homework sections that you did. So the work here, the lecture notes that we completed. And that way I have a chance to grade your homework, get your feedback sent back to you. You'll have an opportunity to ask questions on your feedback before we go to do it in an exam setting. It just seems to be the best kind of process for getting things put onto exam. So anything that's done on this week right here, it's going to be following on to our second exam, which means that's the exam where we're going to start looking into logic connectives, these kinds of things. That'll be kind of a fun section. Other things to mention about this upcoming exam, like we mentioned before, is there's a calculator policy, but nothing too major. I have two suggested models of a calculator. This one is for the more hardcore people that like to type in their stuff with order of operations in mind. This is for people who like to type in the results as just one line and hit enter. All those calculators would be just fine, as long as it's a basic scientific calculator. We're excluding anything that's considered a classification like a graphing calculator, such as the TI-84, those kinds of things. Also, like we mentioned, a formula sheet is going to be provided as the very last page on the exam, and it's this sheet right here. So the formulas I decided to put in are mainly lots of definitions. I guess we could call this a strict formula, the one below. But these are the major things that we were taking a look at from those sections by section basis. So as you study for exam number 1, this is an important document because it's going to inform you what is provided on the real exam. I literally just copied and pasted that as the last page of our real exam 1. And also inform you the things that you have to be ready to go, have memorized for the purpose of that exam. So that's the last page of the real exam. Then down below, I gave two different versions of a sample exam. Version 1 is lecture notes converted into worksheets. And maybe that doesn't sound too exciting, but the value of that is, when you look at the original lecture notes, there's a lot of noise there. It's really actually hard to study that stuff unless you're just looking for a step-by-step solution. That's not too helpful either, because if you're studying for this content, you need to get in the practice of just writing out all your whole own solutions top to bottom without looking at a guide. So what I did with these notes right here is I went to a section by section basics, took out all the formulas, just put in an ample white space. And these are the kinds of problems that would make a decent exam problem on the real exam 1. Again, I can't ask literally this problem right here, but the modifications to this would make a decent exam problem. So that's what these notes are all about. But because these are problems we have seen before, if you have a really, really good memory, they may not be as exciting. So a second version is down here as well. So you can take a look at version 2 for more pretty similar problems as well, just extra practice. Downside of version 2 is I don't have the solutions to that yet. The solution to version 1 is just going to the Moodle website and clicking on one of those sections to see the solution. I do intend to get these posted as soon as possible, hopefully before we get to the weekend, to be as useful as possible for studying. But that's pretty much how our exam is going to be. It can't involve every single problem that we looked at from 2.3, section 2.2 through 2.4. So either document you're looking at is going to be a reasonable sample exam. All I'm trying to do is get a representative set of problems and concepts out of this to form an overall exam. It's not going to be a very long one. And if you've been up on the homework, caught up on these sections here, it'll be more of a formality is what it'll feel like. But I'll turn it over to you folks. Any questions at all about our upcoming exam?
Sorry for the delayed question, but for most exam one, and I guess the homeworks as well, um, will there ever be any reason to not answer in like integer form or like round numbers? I guess I don't know. That's a good question.
Oh, so you're meaning the output answers like you saw in the homework? I
Yeah,
think that
yeah,
that you're expecting on the real exam are going to be pretty similar to those as well, where a lot of the answers were ordinary integer answers, not a lot of messy answers like 17.5327 or some stuff like that. So
gotcha.
the problems that I'm writing are going to be pretty clean, like what you saw here.
Okay, all right. Thank you.
Yep, absolutely. Did I totally answer your question, just to be sure?
Yeah, yeah, you did.
Gotcha. I think what sometimes does happen, the kind of idea you're mentioning is sometimes in math classes, when people go to write out their lecture notes, sometimes they're pulling in problems from literally a textbook. And those are nice problems where the numbers just work out beautifully. There's no weird issues with approximations and so on. But then when people go to write their exams, they're custom problems, and suddenly the numbers look a little bit messy or extremely messy, or maybe a lot of extra algebra out of nowhere. But I tried to write the exam that's going to be very similar to both these problems as well, in addition to the actual assignments that you've been working on those section by section basis. So the numbers shouldn't feel like they are out of left field, out of nowhere. They'll feel like you're still doing these kind of exercises. And just also to go along with that same kind of comment, pretty much when I go to write out all the homework sets that we've gone through, these as well, all the lecture notes we've done, and then finally this document here, the moment I write the actual exam, I double check my problems by solving them. It's a good idea if you're going to write an exam, you should solve it first before you send it out into the wild. But I'm also looking at these documents as well as your homework exercises to just make sure, did we do something like that? Is this problem out of left field? Did we even do this concept? So I'm making sure everything that's actually on exam one is stuff that we've seen possibly three different ways. Lecture notes, the homework exercises, the reading, or maybe four different ways if you're looking at the additional problems here. But other questions that folks have on exam one? Yeah, go ahead.
So just going back to the worksheets made from the example problems from the notes, are there an easy way to check the answers as well, or you just go back in the notes to do that?
It'd be back into the notes, yeah. Not a super easy way, unfortunately, but it'd be clicking on these things and scrolling through to that right exercise. So that part is a little bit annoying. Sorry about that.
Oh.
Good to hear. Other questions so far? Okay, well, the exam is going to be next Monday. You know, honestly, this is a little bit confusing for a class like this one. Let's go right back to the top of the Moodle website. Because next Monday is an exam day. The people in this section here are going to be mostly in the classroom taking the exam. And I did contact people on a person by person basis. So if you have a different testing center, that is official now. And for the most part, people in this section are going to be taking an exam at a testing center, either the Pocatello Testing Center, Idaho Falls Testing Center, or otherwise to be worked out. That means when you come back on Monday, if you're the person in section 44, the online section coming in through Zoom, it's a little bit confusing because we won't actually have class that day. It's just going to be an exam day. So for the folks that accidentally log into Zoom on my classes where that happens, it's an exam day. Sorry about that. That's just my attempt to get ahead of that weird confusion. Well, we'll talk a little bit more about the exam when we come back next class, as well as I also wanted to mention on the day-by-day syllabus, I don't really have a lot of time, well, no time at all injected for reviews. We are supposed to be in chapter 3 around this week here. But if questions do come up that you would like to discuss at the start of class, that's open to any class, even the ones right before an exam. I'm happy to discuss exam review questions as well when we come back on this day on Wednesday here. So just because we don't have an official review day built into the schedule doesn't mean you're ever prevented from asking a question. And when I call for questions at the start of class, I really mean anything, something out of the lecture notes, something out of the exercises, or otherwise, I'd be happy to discuss.
So
But let's get back to where we're at. Sorry, go ahead.
if I had a question on like a homework correction, would that be appropriate now or should I wait until like after class?
I would say it's more kind of up to you. I would be happy to discuss a homework correction. You would have to be comfortable talking about your problem and the error or anything like that around it. If you're comfortable with that, I'd say that's totally fine to discuss those.
Yeah, so it's on homework two, the first one. It was negative 42 mod 17.
Oh, gotcha.
I answered
So
as negative 8 and it was marked wrong.
that one's a very good question. Let's do it down here. It deserves to really give some time to take a look at it. So this one was from, that must have been section 2.2 homework. And we were doing, what was the modular arithmetic on that one?
It was negative 42 mod 17.
Mod 17. Awesome. This one is actually a pretty conceptually tough question right here. And I think the reason for that is the way we explain modular arithmetic makes sense if and only if that's a positive constant. It's not that we're doing anything different if it's negative, but we need to kind of shift our analogy. When this is negative, what we're really dealing with is multiples. So let's take another look at this from a second point of view. First thing we would do is look at this thing. We're interested in the multiples of 17, so let's place some down. We have 17, 0, negative 17, and I had a sensation that I was going to need a calculator today, so here we go. So negative 17's second multiple going this direction would be negative 34. Let's do it again. Negative 34 minus 17 gets us to negative 51. So we're way out here. And then the answer to this modular arithmetic here is going to be the nearest multiple that, excuse me, it's going to be the distance that exceeds its nearest multiple, looks like negative 51. So we would place this value, negative 42 here, not placed perfectly necessarily. And now let's sort out the arithmetic here to see how we're going to correspond to what's going on the number line versus the modular arithmetic. And honestly, this is confusing enough. This is a good one to go by formula. N mod k is defined to be n minus k multiplying the floor of n divided by k. And this formula the author supplies is valid whether or not n is positive or negative. The author gives another great explanation about this under the exercises where he first introduces that formula. He does a negative one. And I think his take on how to think about that is great as well. This is similar in spirit. We're just using the number line as an extra visualization. So in this problem, we would go negative 42 minus 17 multiplied by the floor of negative 42 divided by 17. So let's throw that into the calculator. So that comes out as negative 2.47. And some change. Let me put in a dot there to say we've got an answer accurate to 2 decimal places. Now, once we go to sort this out, we are getting a negative 42 minus 17. The floor of this integer here would be negative 3. Some more calculator work. Let's make decimals work hard for us today. Now, negative 42 minus 17 by negative 3 gives us a value of positive 9. And now my claim is, let's double check this on the graph. We produced the graph first after all, before computation. My claim is that the distance from here to here is exactly that value 9. So let's double check. Negative 51, negative 42. Yeah, there's a separation of 9. And so the analogy here is that 9 is the distance that negative 42 deserves color coding because this is kind of strange for sure. The distance at negative 42 is away, let's say not is away, the distance that negative 42 exceeds, because we're thinking going to the right. We're not talking the closest distance to the next multiple. We're talking distance away from the prior multiple. Exceeds the next multiple, or let's say the prior multiple, of 17. But when we did the negative modular arithmetic, the prior multiple of 17 you were concerned about was that negative 51 right there. So when we go negative into this location, and folks have mentioned before that this is actually sensible in computer science as a kind of error checking, I think you mentioned before. But for the purpose of trying to relate this to remainder after division, really weird concept. This is pretty much the visualization anytime that negative comes up. But does that help out with that concept there?
Yeah, it just, when I typed it into my program, it gave me negative 8. Just not quite following that, but
I know I've heard that more than once. I think another person mentioned that as well. It looks like it depends very heavily on the program that you're using. We tested this one out on wolframalpha.com, so I'm assuming this is the same in Mathematica. It does return 9, but you're not the first person that mentioned other platforms are giving different values. Really weird on this. So watch out for these when it comes up in, say, an exam setting. What the author is going for is through this formula and this interpretation here. But looks like it's debatable. That's kind of unfortunate in a way. Depends on how people implement this into hardware or
thank you.
software, where yeah, absolutely. Any other questions or comments about this concept here? Okay, I would say this is the most asked about concept of the class so far. So that's kind of cool in a ways. That kind of informs me. Definitely that's a good one to make a big deal out of next time I run through this class. I'll try and keep in mind too that other computer software make this even more confusing when there's differences on how it's implemented. But back to the Moodle webpage. Any other questions at the moment? Okay, and just going back to what Christian was saying earlier, you're absolutely welcome to ask questions about prior problems, like the ones that we're looking at here. Honestly, when you get your homework back, getting your homework back doesn't really help you out unless you're really looking at the problems that you missed, understanding why. And if that understanding fails, you can either come to office hours, bring the problem to class, all terrific options. Emails will work out great as well, just whatever works the best. Well, we're about to finish off section 2.5. This is content that's going to occur on the second exam. Then we'll walk into chapter 3, a pretty exciting chapter on propositional logic is where we're starting off on. The reading says read both sections 3.1, 3.2. That seems like a little bit punishing, but in our book, the 3.1 section is usually a 1 to 1.5 page short blurb on why this chapter is really fundamental. Every chapter is fundamental, according to the author. He's got a great write-up on sections 3.1. But then after looking and reading this section 3.1, I was reading it on Sunday, completed the reading, went to do the homework exercises, and I did find my first snag on this book. It's a terrific book, but sometimes with these free textbooks, the homework sets are usually sometimes not always the best. Chapter 2 is awesome. I liked all these exercises here. But in chapter 3, there's some problems with the actual exercises. There are a lot of concepts here about logical connectives, about propositions, compound propositions, and such. But when I got into the exercises, there's not a lot of supporting material in actually learning that stuff, the content of the book. The reading is great, but the exercises, you'll find them by clicking on this link right here. Click on this PDF here. And this is what the homework set looks like for section 3.2. Or hang on, what did I put in here? Oh no, that's my notes. I'm gonna have to fix this in a moment. Let me put a little note to myself. I had a PDF of all the exercises. I think I just got mixed up in which one I was putting in there. So I need a big reminder. That deserves all caps, I'd say. Fix. the exercises PDF in section 3.2. Well, I had a lot I was going to say about that, but darn it, I'll come back to that once I get those exercises actually in order. Since that is a little bit damaged here, I think probably the best thing to do on the Moodle website for the moment is hide my mistake. Here we go. I'll get this fixed up as soon as I can. I'll have this, when this is unhidden, the right actual PDF there. But it's going to be a mix of some custom exercises that actually support the content of logical connectives, and then a few exercises that were from the book that did look like they were great ones. But sorry for that little weird issue there. We'll come back to that once we get those fixed up. For the moment, we're in section 2.5, about to finish it off. And so here's where we left off. Well, not quite there. Here's where we left off before we went on the weekend on last Wednesday. We're looking into one-to-one functions, but one-to-one functions are usually not thought of in isolation. They go along with the concept of onto functions. So just for a quick reminder on how those go, we say a function is onto if, when you go to the codomain, every single element in the codomain, we have an element A in the domain itself, for which the function maps into that element in the codomain. Or another way to say it is, a function is onto if the codomain is the actual range of the function. Every element there is hit, as our author often likes to says, by f of something. So that's what makes it onto. And part A, this was a weird defined function, but we found it is not onto whatsoever. We did f of 0, it mapped to positive 2, so we highlighted that element. We calculated f of 1, it mapped to positive 3. Then f sends 2 to 2, that's duplicating. It maps 3 to 3, duplicating it as well. Because these two elements then were never hit on by any pre-image here in the domain, we say that this is not an onto function. The range is just 2, 3, not equal to the codomain, in other words. We turned it around a little bit and looked into functions, say, like sine and cosine. Ideas with these functions are, we write out sine. Sine has a range that goes from as low as -1, the second coordinate there, up to +1, second coordinate on this one. So when we define a function from R to R and call it sine x, that cannot be an onto function because here's one element in the codomain that is not hit by any x element in the domain. But if you refine this and change from not necessarily sine to cosine, the function here is irrelevant whether it's sine or cosine. But if you limit its range to -1, +1, then every element here, no matter if we call it sine or cosine x, every element from -1 down here to +1 up here has an element in the domain that maps to it. So we say that this function is onto, whereas this one wasn't. Only difference was the codomain here and here. Any questions at all, folks, about the onto definitions? Okay, and again, for the folks who are like to say it the French way, you could say surjective or onto, but you do not have to unless you prefer to. Then going down to the next concept, if there are surjective functions, the French would say injective for the other class. Injective functions are the ones that we call one-to-one. One-to-one functions are great as well. These are both really important properties. We say a function is one-to-one if any element you take out of the codomain B, you will only find at most 1A from the domain such that f of A equals B. This at most 1 is important because maybe you found an element B in the domain such that no A maps to B whatsoever. That's okay, it doesn't violate one-to-one. If you find exactly 1 that maps to B, you might be one-to-one, except this has to work for any element in the codomain B. There will always be at most 1 element that maps to it. Said in an entirely different way, but equivalent, is if you take 2 elements, A1, A2, coming out of the domain, with the stipulation that they're unequal, then these values, f of a1, f of a2, they're in the codomain, and they cannot be equal if the function is really one-to-one. You could even turn this idea around if you would consider the contrapositive. That's getting into section 3.2. We'll look at these under a really sharp logical lens when we have more logical connectives, quantifiers, and all that fun stuff to really digest what these statements are trying to say. But for the moment, we're practicing with what we've got, and we're going to just see if each one of these functions below is one-to-one. These functions defined in this kind of way with a finite domain, really all we need to do is do some evaluations. If at any point one element maps to the same element in the codomain here, we'll say it is not one-to-one. So the strategy when this comes up is just do function evaluations starting at f of 0 and working our way through. But we don't have to do all of the function evaluations. We stop when we have indications that tells us something is not one-to-one. So starting off the mapping, take f of 0. That means 0 plugs here, and the output is 0 mod 8. But 0 mod 8 is a normal operation. This is the remainder after division by 8, which is 0. And when we go to our next step, we just have to make sure we don't see 0 again. Not that it's a bad thing, but if we do see it again, it means the function is not one-to-one any longer. So go to the next domain element, map 1. Back over here, that's 1 cubed minus 1, so we're back to 0 mod 8. This one is equal to 0, but that means we have found that two function values occur despite the inputs 0 and 1. They are not equal, but the function outputs were equal, violating this right here. This alone tells us, because of that match right here, f is not 1-to-1. Since two elements are mapping to just a single one right there. But any questions at all, folks, with this one here? Okay, so in part A, we just stopped after mapping 0 and 1 because this is enough evidence already. We're not dealing with a one-to-one function. Let's try it again in part B. Same sort of function, except there's been an adjustment right here. Still mod 8, but that adjustment too can make all the difference. It might be one-to-one. Let's see if it really is. We have to do the mapping to test this. So take f at 0 like before. And like before, that's just 0 mod 8. So we get an element of 0. Next, do f at 1. Plugging 1 in here is getting us a 1 minus 2. So now we're in this uncomfortable land of -1 mod 8. Whenever this comes up, I'm always very tempted to just break out the formula. So let me do that right here. This would be -1 minus 8, multiplying the floor of -1/8. So the floor of -1/8, that's -1.25, or excuse me, -0.125. That would just give us a value of -1 right here. So that's -1 minus 8 times -1. So we have a value of 7 altogether on this one. That definitely is in the domain, but we should expect that it is. If you do a mod 8 operation, then your codomain right here is going to go up to 7. There's no possibility of getting an 8 if mod 8 comes up. I think I must have accidentally called that the domain. That's the codomain right here where the red dot is. So still, these are distinct elements. This mapping F has the potential to really be one-to-one. But to know for sure, we have to do just 2 more function evaluations. So we take f at 2. That would be 8 minus 4. So that's a 4 mod 8. 4 mod 8 is the remainder after division by 8. Division of 4 by 8, so we get 4 there. And here's the last element, f at 3. Would be, let's see, that's going to be 27 minus 6, so 21 mod 8. Any volunteers for the operation here, 21 mod 8? Absolutely. We would have 2 by 8 is 16. So the next distance to get us to 21 would be by 5. And so that means we got it, folks. We need to make a conclusion here. We've definitely mapped everything over. Would you call this one-to-one or not one-to-one?
One-to-one.
Absolutely. Good call, Dinesh. Because all of the outputs, which are 0, 7, 4, and 5, they're all distinct. That means this never occurred where we map this to the same value when the inputs were distinct. We'll say, therefore, f is an onto, is an 1 to 1 mapping. Don't know where onto came on there, but now that I mentioned onto, let's think about that as well. Was it an onto mapping?
No.
I agree with Corbin. There's a fast way to answer that, although it wasn't part of the question, so I'll use this pencil tool just to say additional comment. F is not onto. It was great that it's 1-to-1, but it feels up being onto just by that element right there. Not onto, since f at x equals 1 cannot be solved for any x in the domain. And we tested it for real. We mapped every element of the domain. We never caught a 1, so this cannot be an onto mapping. Another way to think about this, however, is if there are 8 elements in the codomain and it's finite, and your domain is 4 elements and finite, you never had the possibility of being onto. The only possibility for onto with finite domain is if right here, there's exactly 4 elements. That would give it at least a chance. Which makes all these problems really kind of strange in a way, because how often do you really have a function with a finite domain like this? Usually your domain is infinitely numbers like this function f. So think about parts A and B on example 4 as just a way to think about what is one-to-one. It was more about the definition and just more practice with modular arithmetic, apparently. Although this may not be a very good exam question right here, it's still a good question to think about what does one-to-one mean when you have infinite domain like this one right here. We really just have to work from the definition. So let's screenshot it. Come down here, and we'll test this one for being one-to-one. What should we do? Well, there's lots of approaches. We can think of the core definition, or go with the statement here where it says alternatively. We could say for any A1 and A, A2 and A, with A1 not equal to A2, f of A1 equals f of A2. And then you can turn this around again. If you want to attack a problem like part C right here, oftentimes we give this approach. Alternatively, again, we could say f is 1 to 1 if and only if A1 equals A2 whenever f of A1 equals f of A2. This is, again, a third way to look at one-to-one, which doesn't feel great if we're trying to learn the concept. But the reason we need that is if we're going to test it up here, this is a great approach. We start by assuming f of A1 equals f of A2. So let's say that here. Assume, I'll call it f of x1 equals f of x2. If we make that assumption, and x1, x2 are fully generic, these are arbitrary values coming out of R, then our goal is to assert next that x1 equals x2. If you can do that, f had to have been a one-to-one function. Now, people really fluent in algebra might say, just plot the function, apply the horizontal line test, and that's great, absolutely. But the reason we're doing it this slightly harder way is f could be a nasty function. It could be from R4, for example, to R2 by 3. And plotting this function is not going to be a great time. I'm not sure where I would even start trying to plot a function like that. I would need to attack it analytically like this through the core definitions. There's no picture here for me to help me. So in case the functions get just absolutely more complicated, this is a great approach. It helps with harder contexts. So we start by assuming function values are equal. We use the mapping to say that means 2 x1 cubed minus 4 equals 2 x2 cubed minus 4. So all I've done is plug x1 into this location on the left-hand side, x2 into this location for the right-hand side. Our goal is to show x1 equals a2, but that's actually possible in this one. Add 4 to both sides. 2x1 cubed equals 2x2 cubed. Divide by 2, x1 cubed equals x2 cubed. Here's where we have to know something about what's going on with these exponents. If this was x1 squared equals x2 squared, we have a problem because x1 squared equals x2 squared implies x1 is either positive or negative x2. This would mean not 1 to 1. We're looking for dead on equal, not positive or opposite in signs, same in signs or opposite in signs, in other words. So the fact that the power is odd here allows us to take the cube root of both sides and assert x1 equals x2, which then and only then implies f is 1, 2, 1. So when we have to look at 1 to 1 again, and the functions get really bad, this is a great approach. And again, think of these other ones as we're just understanding the definition of 1 to 1 to see how it relates in a smaller example. But any last questions at all, folks, on getting through part C? Okay, well, I have one more example on here because I felt that just discussing 1 to 1 and onto and just leaving it at that, I mean, it could work, but it's hard to learn unless you can tie this together with something that's real. So here's my best attempt at an actual application. I really have two applications. My first thought was to do something like this, domain and range for that makes sine x a bijection. But this is purely a mathematical application. So we'll come to that one. And first do this application, which is a US government application. So first let's collect our definitions. Bijections are very interesting functions. For a bijection, we insist that the function f is 1 to 1, and onto all at the same time. So that means this codomain B here is also the range as well. And every element in A is going to map to a unique element in B. If that's the case, you can reverse the mapping now. If we do that, we'll call it the inverse of F, and every bijection function will have an inverse. In other contexts, these bijections are sometimes called isomorphisms. Let's say here, bijections are sometimes called isomorphisms. Let me spell it correctly. Where this iso part right here means same, and morphisms means form. So in a certain sense, when we say we have an isomorphism, it means we can relate the set A to the set B through a mapping with these two properties so that it's a way to translate from one to the other in this very specific way. Isomorphisms play a really strong role in algebra, and so that's one of the major reasons why to talk about a bijection in the first place. So here's a function that we have defined in example 5. It maps C to D. These are just sets, and they can be anything. We're used to sets of real numbers. But that's not required, and it's not always practical depending on the problem you're working on, because our set C is defined this way. It's a collection of all elements X, or people X, where X is a citizen of USA. So that's how C is defined. And D is something entirely different. It's a type of string. We're putting together 3 digits, 2 other digits, 3 more digits, so some definite structure here, where the digits A, S, G are just 0 through 9. Anyone see what this would really be as a set, as it relates to the US government?
Social security numbers.
Absolutely. This is, well, it's the set of social security numbers. But if you really look into that, certain social security numbers are actually banned. There is no social security number that starts with 000, for example. That's really technical. So if you think of this as a set of all social security numbers, that would be okay. You're doing the same kind of problem in spirit. But just know that there are very interesting things going on with this set of all social security numbers. In fact, you could count all the possible arrangements here if you really want to. It's just under 1 billion. So at some point, we're going to run out of social security numbers. The system will change because if a person dies, it's not like we reassign that number. It's not like a telephone number, for example. So by knowing what that set D is, however, like you mentioned, it explains what the mapping F is trying to achieve. F maps each person in C. We know it's each person who is a citizen of the United States of America, but that'd be redundant. I'll just call it C for short. It maps each person in C to a social security number in D. So it's a massively important mapping. It's something that people spend a lot of time and energy looking into and constantly updating. But a couple questions are, is this a one-to-one mapping?
It would be a one-to-one because each person has a unique social security number. They can't have the same one.
Exactly. It'd be madness if one social security number could be 2 or more people, right? So one of the very strong requirements of a function like this in government is, just like you said, it absolutely has to be one-to-one, or the whole system has just totally failed on us. So let's say here, yes, this must, that's always a strong word to write down, but it must be one-to-one. And just to capture the essence of what you said, so that each person in C has a unique social security number. And that could have been said in a different way. You could also said it must be one-to-one, so that every social security number in D maps to a unique citizen in C. But we wonder if that's really the case, because this cannot be onto as a mapping. Like we mentioned, this is just shy of 1 billion different elements that you could put inside this set. There are social security numbers, in other words, that are just not taken up because that person hasn't been born, put into the system with social security numbers. So it cannot be onto. We have to say here, since social security numbers in D are available with no assignment, from a person in C, the set of all these people up here, F is not onto. So as a system that we wrote down here, it's not an onto mapping because this is a pretty big set. It's got more elements in here than we've had people that have been alive and people who've been around since the Social Security system has been in place. But, this is not as big of an issue as it seems, but it does cause a problem. The mapping, as we defined it, cannot be a bijection. It's 1-to-1, but it's not on 2. So we'll say here, it is not a bijection since F is not on 2. And that's really okay in a certain sense because there is a bijection there somewhere. It's just that D is not the range. In fact, the range is changing all the time as people get put into the system, but presumably the US government does have a system of all of the Social Security numbers. They could find the range and just place it here on the mapping. Again, it gets updated all of the time, but that means there really is a bijection. You just have to shrink down the codomain until you have the set of all Social Security numbers deployed in existence currently. That means the mapping is changing all the time, but there really is a bijection somewhere. You just have to find it. But this is our overall application style of a question that addresses ideas with 1-to-1 and on-2. They're really very fundamental, unique things that we think about all the time. Just usually we don't write them down this way when we're thinking of those thoughts. Well, any last questions at all, folks, with this application here before we turn to the next? Okay, that concept of what we mentioned here, that the mapping is not a bijection, until we put the range right here, is kind of what's going on with a lot of problems you might have felt were strange in algebra. For example, if you take a look at the function sine x, almost the right function, just from the graph alone, we mentioned this is not a 1-to-1 function at all. For example, this height right here, height of 1 as an output, that's in the codomain, or the range you could say, it's achieved infinitely many different times. So since pi over 2 and 5 pi over 2 both map to 1, already it's not 1-to-1 whatsoever. That means sine x is not a bijection, and that means this function here has no inverse whatsoever. Yet you can write out arc sine, let's say 1, get a value out, that's pi over 2. And where did arcsine come from? Arcsine only exists if there is a real bijection somewhere, a function that came from here that is 1-to-1 and on-2 all at the same time. That's what's going on with this really short application right here. If you want to force a function like this, which is not even 1-to-1 in the beginning, you can do it. You just have to find the right domain and range to make it happen. And here's one way to do this. You could say go from, let's maybe go from negative pi over 2 less x less pi over 2. And on this massively reduced domain of x, notice what happens with this function. This is 1-to-1. It's strictly increasing, so all the second coordinates are only ever hit once between -1 and +1. And so that does the job for us on this problem right here. Again, probably really short application after the last one, but just tying into the idea of there's not always a bijection when you look at the overall function. If you make changes to domain and codomain, a bijection can enter the problem. And we all know that sine inverse is a very useful function, so this is an important concept. But it was meant to be kind of a short application, so let's answer the question by doing it this way. On the domain from negative pi over 2 to pi over 2, y equals sine x is 1 to 1 and onto with range from -1 to +1. Then from this, we define the inverse, either call it arcsine or just sine inverse x. It's a totally new function, but notice what it does. We had a domain over here. We have a range over here. And when we go to sine inverse, this is the domain from -1 to +1, and it maps into, this is the range, -π/2 to +π/2. So in defining the inverse function, we literally swap domain and range because we're changing the role of x and y as a coordinate on every single point here because it's now a bijection. Couldn't do it in the last problem just because it wasn't on 2. But these are the just last two applications to think about, 1 and 1 and on 2. Any last questions or comments, folks, about either one of those concepts? Okay, well, we did it, folks. That's the end of section 2.5, and now we're finally closing out chapter 2. That means we're getting into, I'd say, the pretty fun part of this book. We're going to go into chapter 3 on logic, and it starts off in section 3.2, dealing with propositions and the logical connectives. I'd say the reading in section 3.1 is probably one of the best forewords to a new chapter I've seen in a math book. It gives you very good reasons of why you want to study this kind of stuff as it relates to mathematics, computer science, and other things you're probably going to see as well. So here's where that section starts off in earnest. Let me go to 3.2. Recall back all the way in the first day of class, section 2.1, we were looking at the various data types in section 2.2, and we had this one example that never tied back into the exercises. It was just something the author mentioned. Boolean values are something that is either true or false, and now it makes a comeback here in chapter 3 in section 3.2. Well, aside from the Boolean values, we assign a Boolean value to a proposition. A proposition has to be a statement that can either be designated as being true or false. So nothing in between. And because of that, it can't be a question. You can't assign true or false to a question. It can't be a declarative statement as, say, like, come to class on time. You can't put true or false on that. That's just a command or something like that. So propositions have to be things like these, whether you can assign either truth or false to a statement like this. For example, I think I gave away part of the example one, but that's all right. If we have a right proposition and you can assign either true or false, then we assign to the proposition P the truth value, which we refer to as the Boolean, all the way back in section 2.2. So when we look through these, example 1 is just asking us to determine which statements are propositions in the first place. And if it is a proposition, we'll assign a Boolean value to it. Again, I think I kind of gave away part A, but this one is absolutely a proposition because the statement, the integer 1, 2, 3 is prime, is truly either true or false. So let's say here, this is a proposition. Now we can hit it with a Boolean value. Has anyone spotted if this statement is true or is it false? So I'm saying false. I agree. It looks like 3 would divide that. So it's divisible by 3. Let's say false. Divisible by 3. So it cannot be prime. If it were prime, only 1 would divide it evenly and 123 would divide it evenly. But we found a counterexample to that. Since 3 divides, whole statement, we assign to it a false. Well, that's our first problem in chapter 3. Any questions with that one there, folks? Okay. Now this one down here, I'm tempted to just say false, but that's not necessarily the right thing to say. This one's not a proposition. It's just a question. So in contrast to this one, this is just an ordinary statement. That's what makes it a proposition. But the moment it's a question or a demand, Here we'll say this is not a proposition. You can force it to be a proposition. You have to just take one step. Now it is. It's a statement that's either true or false. We're not asking a question. We're just writing out a statement. This would make it a proposition. We would assign false to it as well. But as it stands like this, again, it's a silly example, but it's just in stark contrast to part A, so we can tell the difference of what we mean by a proposition and what would disqualify it. Asking a question in the statement absolutely would disqualify it. Well, one more to go. This one is a proposition. It's just a statement about relationships among sets, and it's either true or false. So we'll say this is a proposition and what Boolean would folks give to this one? Would you say true or false? It's a tricky one because this is a subset relation, right? And it's also just not nice notation. We need to know what that Z means and that Q means specifically. But let's put in some little work here to help tie this together. Z is a set of integers. Q is a set of rationals. It's a proposition because this subsetting relationship, subset equals, is either true or false, but its falsity or truthness is kind of up in the air. Let's check it out. Anytime you're trying to investigate if a subset relationship is true, it always goes this strategy. Let X be an element of Z. So we have an integer. We need to work in full arbitrary here, so it has to be any integer. My argument can't be just for 5. It has to be for anything at all. So here's the full argument down below. If you're working this argument, you might have actually grabbed an element like this. 5 is an element of Z. Here we're working by an example just to get our mind in order before we work in full generality and to investigate this relationship being true or false once and for all for any X whatsoever. But by the example, 5 is an integer, it's in Z. What would make it irrational? It has to be rewritten as a fraction, and we know 5 is also equal to 5 over 1, which is automatically an element of, let me try again. Sure, it's an element of Z, but this qualifies it for the element of Q, the set of rational numbers, because any integer whatsoever can always be filled and promoted to a bona fide fraction in this kind of way, even 0. So it's weird, but as long as you're not putting 0 in the denominator, well, absolutely allowed. So back over here, we could say let X be in Z. Then X is an integer. And so X over 1 is a fraction. Now this is telling us if you pick an integer, you can write it as a fraction, which tells you it's absolutely included in the set. So we would say, this shows X is an element of Q, the set of all rational numbers. And that's just what the subset relationship is about. Any element of Z has to be included in Q to make it a subset. So that means we can say true. On the right, this shows X is in Z, X is in Q, and so the integers is a subset of the rationals. So we have a true statement there. I used subset equals as just like a big overall statement. You could have used a proper subset inclusion here, dropping that symbol, and that would have been the same argument. But I decided just to keep the notation the same. So we did it, folks. We really did a couple things in part C. It's a proposition, but it's a complicated one because it's relating set theory back in the same time. However, when you go through this section 3.2, you really want to have set theory kind of pulled up in the back of your mind, because when it comes to set theory, this was in section 2.3. We spent a lot of time here for good reasons. In set theory, the things that are going to come back are This, the complement of a set, we're going to call the negation of a proposition. This one, the union of two sets, we'll call the conjunction of two propositions, P or Q. This one, the intersection of two sets, we'll call P and Q, for example. So all these kinds of things get related back. And in fact, there's something strange going on with set theory as it relates back to propositional logic. There is a type of isomorphism between the two systems. They work almost identically in the right certain sense. So keep set theory in the back of your mind as you work through these. It's not just a strong analogy. It's pretty much what's going on in these kind of concepts. But let's go now to the next fun thing, the logical connectors. So we have the not, we have the conjunction and we have the disjunction or. So whenever you see this symbol, think not P or the negation of P, that's related to the complement of a set A relative to some universe. In fact, it's even written similarly. The next interesting one is and. So we write out this way, P and Q. It's true when both the propositions P and Q are true. If one of them is false, one or the other, the whole overall compound proposition now is considered false. But we want to relate this to intersection. It's a very powerful way to think about these two. They're doing in a real sense about the same kind of thing, just different systems. Next is the or statement, written in this different kind of way, the disjunction. This one is tricky because when we say or in English, any statement that has or, we may not be thinking of this sort of or. This one is considered the inclusive or, in other words. It's going to be true when either P is true or Q is true, or even when both P and Q are true at the same exact time, even though that's not how we usually think of or in ordinary speech. So this one, we want to relate the or symbol here to union. We say a set is in A union B if it's in one set or the other. That's where the or comes in. We say an element is in A intersect B if it's in one set and in the same time in the other set, and that's the relation there with and. And we say the complement A is a set of all elements in the universe not in A, and that's the time with the not operator right here. So those are our logical connectors. It's the glue that's going to take simple propositions like these, 5 by 2 equals 4, and turn them into big statements, full-on English sentences, and so on. So that's what we're going to start practicing right away. We'll get a better view of what these are really doing when we go and look at them under the lens of the so-called truth table. But first, this example is just practicing with a new notation. Again, the reason I wrote a custom set of exercises for section 3.2 was there was no problems like this, and I think it's hard to absorb all that material unless you practice with it somewhat. So we have custom exercises in that homework set to support these definitions here. Well, any questions at all, folks, with those 3 definitions in a row here? Okay, there's really a lot going on with this kind of stuff, especially when we get the implications and the next sections, the quantifiers. But we're building a big system, so here's where it starts. Well, there's the next step in that process. We have 2 propositions. It is raining, that's a statement you can assign true or false. Same with it is cold, so that makes them definitely 2 propositions. And we want to start connecting these with our operations up here. But all we're doing is writing out what this would say using ordinary words. I'll go first. If this one says not P, relating this operator, it's the negation of the proposition P. So we would just say the statement here is, it is not raining. And that's all the only modification we had to make to this proposition, just related through the negation. Well, that's riveting stuff. Any questions, folks, with that first one? Okay, let's try this out again. How would y'all read out this statement in ordinary words? Any volunteers to just say this out? Absolutely. The statement was, it is raining. And it is cold. Now, just a warning in these notes, by the way, sometimes these statements, when we put them together, they can seem silly or weird. That's okay. We're not too worried about, is this overall compound proposition true or false? We're just playing with these connectors right here to see what the symbols are saying once we start using them. So same one with this. You always want to think of this as a not. Every time you see that, think and every time you see this one, think or, and then you're going to be on the right track. So for this one, P or Q, really it's the same statement. We're just throwing an or in the mix. We'll say, it is raining or it is cold. Again, we have to be really careful when it comes to, if you're investigating the truth of this statement in ordinary English. In ordinary English, when we put an or there, we often are thinking an exclusive or. It's one or the other, but not both. But the moment we put that down, this one's inclusive. You don't have to say or both every single time the inclusive or comes up. You can if you want to be hyper specific. There's no harm in that. In fact, it could be beneficial. But it's a foregone conclusion, so if you don't even say or both, it was implied if it came through that operator there. We'll have a new one for exclusive or, but we'll wait for a bit before we get to that operator. First, any questions at all, folks, with this pretty much an introduction of these connective operators here? Okay, they're called either logical connectives, connective operators. The thing we're connecting is propositions, making one overall statement, sometimes several propositions at once. But if we're investigating the truthness or falseness of these propositions, once we've compounded them together with the connectives, then we really have to look at these definitions really hard and build out our truth table so we can be efficient. That's what we're going to be doing on this next section, example 3. We may not build all of them. We have a new one to take a look at, the exclusive or. We'll get started today on building out some truth tables and come back here when we're on Wednesday's class. But first, let's talk about the exclusive or. The exclusive or is written with this funny looking symbol. Sometimes that symbol is referred to as a direct sum symbol in algebra classes or other contexts. But here we're using it for exclusive or. You can either say exclusive or you could say or write XOR. Either way you say it is going to be understood as this one right here. So exclusive or gets around the problem that we had with ordinary English. Sometimes the thing you're trying to write out is P exclusive or Q to mean either one of P is true, or excuse me, one of P or Q is true, the other is false, and so on. So this direct sum operator, P or Q, but it's an exclusive or, it's false when both P and Q are true. We're going back to ordinary English with this operator. We want just one to be true or the other. It's also false when both P and Q are false, so that's like the ordinary or there. So we want to assign truth assignments to every one of these atomic propositions, as our author calls them. This is the compound proposition. And if we can assign truths to each one of these values, P and Q, we can look into a truth table for the overall truth or falseness of these compound expressions, not P, P or Q, P and Q, and P exclusive or Q. So let's do that first with not P. I don't think I want to go too far here, so I'll probably go through these here and leave this one when we come back. But here's the truth table. This is a powerful tool for analyzing these compound proposition statements. First one we're going to do is for not P. We're building out a table as it says, but the way we build out the table is particular. We put down the proposition P here, proposition Q here, and the one we're interested in investigating, not P, would go here. Next, we think about what not P does. It does something to, or excuse me, I put too many columns in here. I was thinking P and Q as in these other ones, but it should have been really written out this way. P, not P. I forget that the not operator just takes one input. So we put in the assignments for what P could be. It's either true or false. I mean, that's by definition. It's a proposition. You have to assign one of those values. Then the not P operator will take the statement that was true, force it to be false, take the statement that was false, force it to be true. So if we know the prior truth or falseness of P, we will know the current truthness or falseness of not P. Any questions, folks, with that operation there?
Can I ask one question?
Yeah, absolutely.
So what if one entity is real number and another entity is imaginary or complex number?
Are you meaning for the propositions like the P here?
Right. So if one is like real number 1, 2, 3, 4, something like that, and another is like imaginary number, in that case, how do we compare or like?
Well, to really get into that example, we would have to say what the proposition P is. It sounds like you're saying P is the proposition that, let's say, X is a real number. Oh, that's not the letter B. Let me try again. And you have another proposition such as X is a complex number. So these would be the two examples that you're thinking of right here. Let me know if I'm on the right track with that example.
Yep.
So if we're thinking of these two statements right here, we could put them together into something like this, P and Q. So from this, we would say this implies P and Q. Well, X is a real number, X is a complex number. We would have to know what X is. So let's put in a actual value here. Let's say it's 5i. So this one is going to be, let's make it be just 5. So now if we look at P and Q, we have to think about what is the truthness of P. That's false. 5i is not a real number. It's complex valued. Q, well, that one's tricky. 5 is a complex number because you can write 5 as 5 plus 0i, and it's an element of C, the set of all complex numbers. Its imaginary part just happens to be 0. Kind of unfortunate. But you know, that means when we look at this part, P, it's false. Right here, we're true on Q, but with an AND connector, the whole thing would be false. Because when it comes to the AND operator, both proposition P and Q have to be true at the same time to output a true. Well, if we go P or Q, this one's different because Q is a true statement. That means over here, if Q is true, it doesn't matter what the proposition P was or how outlandish it is, whether it's true or false. One truth right here says the whole thing is true overall. But is that the kind of thought you were thinking about with that question there, Narajan?
Yeah, something like that. So yeah, so if you need to compare like real number and complex number, how do you do that?
What do you mean by
that
compute?
I mean, compare or compute. Like, if I need to compare like 5 with 5i, is that possible?
Oh, I see what you mean. Like, say, 5 less 5i, this kind of
Yeah.
comparison.
Yeah.
Turns out that one is actually impossible. This is a huge surprise. This is impossible since we're used to order occurring in places like R, less than makes sense. But even if you go into R2, less than greater than has no meaning whatsoever. It's really weird. and the space C of complex numbers has the same feature. So this comparison right here is impossible since C has no order structure with the less than operator. So if this is an impossible statement, that means it doesn't really have any chance of this being true. This would just be false altogether. Does that make sense so far with that question there?
Yeah, sure. Yes. And I've got another question. So if we need to compare like between two complex number or between complex number and imaginary number, is that possible?
It's not possible, no, because we can't make any like less than greater than comparison whatsoever with any complex number. But you know what you could do? You can't make a comparison with complex numbers in C. So in C, Z less W has no meaning. And this is true in R2. X less than Y has no meaning in R2 either. But there's a way to kind of fix this. You can say, however, if we go to the so-called modulus in the complex numbers, which we call finding the distance of a vector in R2 or finding the norm of a vector, we can say that the modulus of Z less than the modulus of W does have a meaning. So yes, you can make a comparison like this in complex numbers, but these kind of comparisons with complex numbers, just the numbers themselves with no operation, they don't have any relationship with less than or greater than. So we can't make any relationship or comparison this way in the space C of complex numbers. Same problem in R2 as well. Other questions about that so far? It looks like I ran out of time. Sorry about that. But any last questions about this so far before we call it a night?
That's all. Thank you so much.
If I didn't totally answer your question, please let me know. I'll be happy to get to you on that. If it's a big one, you feel free to send out an email or anything like that as well. I feel like I might have been answering your question, but I could have been just like a little bit off to the side of what you're really asking there.
Yeah, sure. Like I was working with the machine learning problem, and then like in the feature space, I had like a imaginary number and a complex number, and like I don't
When
know
you say imaginary number, you're probably thinking, say, square root negative
Right.
1 equals I,
Right.
but imaginary number and complex number would mean the same exact thing in this kind of context.
Right. So the complex number is the combination of imaginary number and the real number, right? So
Yeah, I'm usually thinking this, the combination of the real part, imaginary part, is the complex number in C. But you know, the I itself is still 0 plus 1 times I, element of C. It's a complex number as well. Sometimes we just call it the complex unit. It just so happens its real part is 0, its imaginary part is 1. Thank you.
Thank you.
Yep. Have a great one, folks.
thank you so much.
Absolutely. Have a great night.
Hey, we were talking about how I used a picture of a matrix for my 2.4
Oh,
assignment.
yeah.
And you gave me instructions for Microsoft, the Office 365, but it won't allow me to like install the apps on my computer. It says that there's no like license
Dang,
thing.
even
Like I
following
can,
the instructions there.
yeah, like I can access the like Word and all the apps that come with the school's licensing for students, but only the
Mhm.
web versions. It won't let me inside. I sent you an email with a picture of what it shows me, but
Gotcha. The web versions should work as well, but you know, I'd be worried about how well it works, to be honest. Usually it feels like it's loses some features as soon as it's an online thing through a browser or something like that.
yeah, that's exactly the problem because I tried to do what you said. I put my whole document into Word, and then I tried to do the matrix part, but the matrices aren't supported in the web version.
That's awful. Sorry to hear that. Well, maybe I can take another look into this. Let me add to my reminder. I'll ask ITRC what their workaround might be for not getting it working on your machine. Any screenshots you can send me might be helpful, but they should be able to tech support this. I don't see any reason why you'd be excluded from installing with that license directly onto your machine.
Yeah, I
So-
sent you in the same kind of email conversation we were having before. I sent you a screenshot of it.
Gotcha. I'll get back to you on that one. Hopefully having a better workable answer by Wednesday.
Awesome. Thank you.
Yep. Have a great night.
You too.
You're usually pretty good at checking your email, right?
Usually, but my class starts here at 6 o'clock, so it's like a email blackout from about 5:30 to now.
No, I think that I was having issues, I think, with my tablet that I've been doing my assignments on.
Mhm.
I don't think my last email was sent. So if you
Oh, darn
haven't
it.
seen anything from me, then I know it's my end. and I can
Gotcha.
figure it out.
You know, one thing that happens, I don't know if you have an iPad, but I've seen this error happen a lot. Something about the iPad email system within the device is just a little bit different, where if you send something with an attachment, it does some post-processing. If you click it off, it actually doesn't send until you turn it back on again, sometimes days later. I don't know if that's what's going on with you or not, but
I will see.
that's something to look into,
You're
yeah.
usually so good about responding, so I didn't get a response. Oh, that's good.
Yeah.
Fast. Hey.
Questions here? Oh, awesome. Thanks.
Really quick, could you help me
Yeah.
out with problem number 12?
Sure.
So for the answer I got 3 squared root of 3 minus 6, but I know it's supposed to be negative 3 squared root of 3 plus 6. Because it's supposed to be positive, but I don't know where I went wrong.
Gotcha. That's always exciting to find a negative sign. Let me see where we are. So 6 secant theta. Then that would turn into 6 tangent theta. Going from 0 to 3. That looks pretty good. Let me see if I can compare with my answer here to find that negative sign.
Checked it using a gravity calculator because
Mhm.
I knew it was supposed to be positive, and the answer I got was negative.
Gotcha.
And I don't know where I went.
This is 7-3. Gotcha. Problem 12. And let's see. Starts at 0 to 3. I went 6. Oh, hang on. On problem number 12, I think that could be the issue. So the substitution for this one should be a sign on that one.
Oh, a sign?
Yeah, that might be what's going on with the negative.